Hi everyone and welcome back. Today we're going to start chapter 4 in our workbooks, which is all about acid-base equilibrium. Now some of the goals for today are, first, we're going to differentiate between two different definitions of acids and bases. We're going to look at the Arrhenius theory, which you probably know from grade 10 and 11, although you may not have called it that. And we're also going to look and introduce the Bronsted-Lowry definition of an acid and base, which is what we're going to focus on for most of this class. As well, we're going to identify what conjugate acid-base pairs are, and then finally we're going to define what amphiprotic means. So starting out here, we've got the Arrhenius theory of acids and bases. And you can see a couple of examples of Arrhenius acids down here at the bottom of the screen. So one acid that you may be familiar with is hydrochloric acid. According to Arrhenius, what made this was an acid is that it broke down into hydrogen ions and chloride ions. Nitric acid below it, again, we're making those hydrogen ions. And so he said that the hydrogen ions in solution gave acids their properties. So acids release hydrogen ions. Now Arrhenius' theory for bases was very similar. Sodium hydroxide is an example of a well-known base. And that hydroxide ion breaks apart. Same with calcium hydroxide. The hydroxide breaks apart, and that's what gives bases their properties. So the definition of a base is something that releases hydroxide ions. Now the Arrhenius theory does a number of really good things. It explains a lot of what happens in solutions. So some examples of some questions. We can classify the following as an Arrhenius acid, base, salt, or molecular compound. So the first one here is sulfuric acid, H2SO4. This breaks down into two hydrogen ions and a sulfate ion. So this is an acid. Xenon hexafluoride, this, no hydrogen ions, no hydroxide ions. This one is not a salt because it is a covalent compound, so we just call this molecular. This next one is a little bit tricky because you can see at the end that I have a number of O's and an H at the end. This compound is acetic acid, so the hydrogen at this just splits apart and we're left with acetate ion. It's an organic acid. For the next one here, we have a very similar format. I've got an acetate ion, but this time instead of a hydrogen, I have a sodium. So it will split apart, but you'll notice that we're not making any hydrogen or hydroxide. So with this one, we would classify it simply as a salt. Now, this one we're going to come back to in a little bit, in a few lessons, but it actually behaves as a base. So if we did an experiment and tried to look at what the actual pH of this solution is, it's slightly basic. So we have nothing with the Arrhenius theory to really explain why. Next one here, we've got potassium ions and hydroxide ions. So this one is classified as a base. And the next one, this is another one where it just doesn't really make sense. We've got this ammonia. And ammonia is just a molecular compound. It's a covalent compound. However, it also acts like a base. So far, we can classify them according to Arrhenius' theory, but we can't explain the properties of a couple of them. Okay, next question here has us doing neutralization equations. If you'll remember neutralization equations from grade 10 chemistry, when we perform a neutralization, we get a salt and we get water as products. So we're going to put these ones together and get our salt and water as a product. So with this, I have lithium acetate and water as product. With the next one, I have calcium iodide as my salt. And I have a couple of water molecules that are going to be made. We'll balance that up. With the next one, I have magnesium phosphate is the salt that's being produced. And this time I have 6 water molecules that are going to come out of that once I balance everything. So there's some neutralization equations. Okay, the third one is a little bit trickier. We're going to have to work backwards. So it says, write the formula of the parent acid and the parent base that react to form each salt listed. So you can see up here, here's the salt, and we're going to kind of work backwards to figure out what our parent acid and parent base are. You'll notice that the first part of this salt, the cation, goes with the OH minus. So with this, we're going to put the cation, the K, with the OH, and there's my parent base. The next, I'm going to use this CH3COO. There's the anion, and it goes with one of the H's from the water. So this is going to give me HNO2. There's my parent acid. Okay, I'm going to do the same thing here. The Cl is going to get HCl. This, on the other hand, is a little bit tricky. NH4 doesn't have an OH. So right now, a little confusing. Not quite sure what's going on here. Guessing we're going to have to start with an NH3, but I don't have an OH, so it's not really making sense in terms of my Arrhenius theory. Okay, my next one here, H2C2O4 and CuOH2. Parent acid for the last one, CH3COOH, there's the acetic acid, and sodium hydroxide as the parent base. So there's some examples of questions with the Arrhenius theory and neutralization reactions. Now there's a few questions there that we just couldn't explain based on the Arrhenius theory. And this is where a better theory came in, and this is the Bronsted-Lowry theory of acids and bases. This theory of acids and bases is where we're going to spend most of our time focusing in Chemistry 12. And seeing as how I've just told you that we taught you one thing and we're actually lying to you in grade 10, I'm going to tell you right now that the Bronsted-Lowry theory actually only explains part of it as well. And if you continue on in chemistry at university level, you'll actually learn the Lewis theory of acids and bases as well. That will help you explain more stuff. But we're kind of moving forward in baby steps. So with the Bronsted-Lowry theory of acids and bases, this time an acid is a substance that donates a hydrogen ion. So it doesn't just split into a hydrogen ion, it actually donates it, which implies that something is receiving it. The thing that is receiving that H plus ion, the hydrogen ion, is the base. And we'll see how this works in a second. So you can see the acid-base reaction down here at the bottom. Here we've got the hydrogen ion, and you can see that that hydrogen ion is going from the acid to the base. So here's the donor, and here's the acceptor. Now with the products, if this happens to be in equilibrium, and why wouldn't it be, because we've been studying equilibrium all along, we end up with a conjugate base and a conjugate acid. So that base, once it's accepted the hydrogen ion, it becomes the conjugate acid. So we end up with a conjugate acid going with the base and an acid going with its conjugate base. So we get those conjugate acid-base pairs. So we're going to look at conjugate acid-base pairs in just a second. So here's an example. What happens when we put HCl in water? So we're going to add the HCl to the H2O. Here we have our acid. This is my donor. And here we have the acceptor, the base. So water actually acts as a base in this situation. So we end up with Cl minus. The hydrogen ion gets transferred from the acid to the base. And we end up with H3O plus. So here's my conjugate acid-base pair. I've got an acid and its conjugate base. Here's my other acid and its conjugate base. Here's where we can finally explain what's happening with NH3. When I put NH3 with water, what happens is the water ends up donating the hydrogen ion. So I end up with NH4 plus and OH minus. So here's where the OH minus was coming from in that previous example. It's coming actually from the water. The water is acting as the acid, and the ammonia is acting as the base. So again, I've got this conjugate acid-base pair. Here's my acid on the other side, here's my base on the other side. And they go together. So two substances that differ by one hydrogen ion are called the conjugate acid-base pair. And this is what I was pointing out before. Here you can see sulfuric acid, and sulfuric acid will turn into a bisulfate ion. That bisulfate ion, because it differs by one hydrogen ion, is known as its conjugate base. Water, if this is my base on the left-hand side, it gets matched with a hydronium, which is its conjugate acid. Those are known as conjugate acid-base pairs. So we've got some more sample questions here. It says, in the following equilibrium, identify the acids and bases and the two conjugate acid-base pairs. So if we look on the left-hand side of this first question, we've got hydrogen fluoride. On the right-hand side, you can see we've got a fluoride ion. So these two go together. This one's donating a hydrogen ion, this one's accepting a hydrogen ion. So this is my acid, this is the base. Okay, we always have an acid and a base on both sides. You can see that the Cn minus, the cyanide ion, is accepting a hydrogen, and so it's got its acid on the other side. Okay, so we've got this one going with the base. There's the conjugate acid-base pair, acid-base pair. We can complete the following table. We know that the conjugate acid and conjugate base will differ by one hydrogen ion. So once I take away an H plus, that leaves me with HC2O4 minus. It takes on that negative charge because we're taking away one of its positive charges. With this one, we're adding a positive charge. So I have HSO3, and instead of 2 minus, I'm going to add 1, and I just get a single minus. Conjugate base of this one, we're going to take away one of those H's, we're going to take away 1 from the charge, so I get 2 minus. And finally, the last one, I'm going to add a hydrogen ion, so I'm going to get H3O, and it's going to take on a positive charge. Now, question 3 says, complete the following equilibrium, which represents the reaction of a Bronsted-Lowry acid-base pair. Circle the substances that make up one of the conjugate acid-base pairs. You can see that the NO2 has no hydrogen ions to donate, so that means that the H2CO3, carbonic acid, must act as the acid. It must be the donor. So it's going to donate one of the hydrogens. It's going to take on a charge of -1. The hydrogen is going to be accepted by this by NO2, and it's going to become HNO2. Because it's taking on a positive charge, it's going to have no charge at the end. So there's the base. Now looking at the pair, I've got a base here, and it goes with the conjugate acid on the other side. So there's one conjugate acid-base pair. You could have circled the other one as well. Okay, last thing that we're going to talk about today is amphiprotic species. Amphiprotic species, you may have already noticed, these are species that can act as acids or bases. And one of the ones that you might have seen already is water. Water is an amphiprotic species because it can accept or it can donate hydrogen ions. When we put it with NH3, you'll notice that it donates the hydrogen ion. So here it's acting as an acid. If we put water with hydrochloric acid on the other hand, water accepts the hydrogen ion, and so it acts as a base. Okay, finally, a last quick check just to make sure you understand what's going on here. We want to write an equation for a reaction between hydrogen carbonate and cyanide where hydrogen carbonate is acting as an acid. So with this one, if it's acting like an acid, it's going to donate. So I'm going to end up with HCO3 2- and HCN. Okay, and this one is actually going to go both ways. We'll talk about that, why that's the case later. Second one, write an equation for the reaction between HCO3- and H2O, where HCO3 is acting as a base. So if it's acting as a base, that means it's going to accept a hydrogen ion, turns into H2CO3, and we have water acting as the acid, so it donates the hydrogen ion. Okay, third one here is circle the amphiprotic species in the following list. Now for this one, we're looking for those that can both accept or donate a hydrogen ion. So acetic acid, CH3COOH, only donates the hydrogen ion. It never accepts an extra one, so this one is not included. H2PO4, however, could donate an ion and become HPO4 2-, or it could accept a hydrogen ion and become H3PO4. So this one is amphiprotic. In C, there are no hydrogen ions for it to donate. It can only act as a base, so it's not going to be one. With this one here, H2C2O4, again, it will donate a hydrogen, but it's not going to accept any others. So it is not amphiprotic. Okay, last one here. This one can donate, because I've just got one up the front. So we could make C2O4 2-, or we could accept another one to become like the compound in D. So it is also amphiprotic. Now, I'm not expecting you to memorize all of these. In the next lesson, we're going to be taking a look at a new chart in your data table booklet, which is called the relative strengths of Bronsted-Lowry acids and bases. If you want to flip to that, you'll find that all of those amphiprotic species are found on the acid side of the chart and the base side of the chart. That just makes it so you don't have to memorize things. So that's it for today's lesson, looking at 4.1, identifying acids and bases. Thanks for watching.